Greetings. Today I'll be talking about finding an area under a curve, the volume of an object formed by rotating a surface, and the volume of a solid with a specified base and cross sections. So let's start with finding an area under a curve. The first and most obvious way of finding an area under a curve, also the most accurate way, will be using definite integrals. So you might be familiar with this. If you have a function, let's say y equals fx, the area under that function on a specific interval, let's say from a to b, closed interval, can be expressed in this form. So let's have an example here. For example, we have y equals x squared, and we want to find out the area under y from 1 to 2. So easily we can just substitute 1, 2 into the definite integral as well as x squared into the definite integral, and we'll get our answer. But sometimes you may be unfamiliar or unable to perform the integration. So you can also resort to geometry. So geometry is a pretty simple way of finding the area under a graph. It's pretty intuitive. For example, if you have this line here, you know that the area under this line will be this triangle as well as this rectangle. So you can easily apply your knowledge of geometry to find out the area under this graph. So for example, you can have the area of the rectangle added with the area of the triangle, and you'll get the area under the graph. Now unfortunately, geometry may be insufficient in cases where the function is not very easily broken apart. So in these situations, you can use Riemann sums. Now Riemann sums, what they do is they help you to estimate the area under a graph. Now these are less accurate than definite integrals, but they work most of the time. So there are a few types of Riemann sums. First, you have the left Riemann sum, where you have rectangles that are where they have the left corner on the points of the graph. So the way Riemann sum works is that the area under the graph will be approximately equal to the summation of all the areas of the rectangle. So you can have any number of rectangles, and however, if you have rectangles that are of the same width, you can also use this formula. This is basically a more mathematically sound way of saying the area of all the rectangles. Yeah. So let's look at this example. I have a set of data here. This is fx, and this is x. So if we use a left Riemann sum with 4 rectangles, due to the nature of the data, we cannot use rectangles of equal length. So instead, we have to make do with rectangles of different lengths. And using this is basically the summation of the area of each rectangle. Note that when I choose the height of the rectangle, I choose the one on the left, not the one on the right, and so on and so forth, and you'll get the area. Now, for right Riemann sums is very similar to left. The only difference is that for right Riemann sums, instead of the left corner being on the graph, it's the right corner instead. And the equation for it is slightly different. We have k equals to 1 and n instead of k equals 0 and n minus 1. So using the same values that we had earlier, we can calculate using the right Riemann sum as well. Just that in this case, we use the values on the right and not the values on the left. There's also middle Riemann sums, which are similar to left and right, just that it's the center of the rectangle. These Riemann sums are usually a bit more accurate than the left and the right, and so on and so forth. This is a general formula. Now, finally, for Riemann sums, we also have trapezoids. Trapezoids are probably the most accurate one, and luckily for us, they are just an average of the left and right. So using the data that we had just now, we can have the average of the left and right, and we'll find out the trapezoid Riemann sum under the graph. So let's move on to volume of an object formed by rotating a surface. So how does this work? You have we know that volume is traditionally the integral of area. So what we can do is we can use our knowledge of definite integrals to find out the area under the graph, and then we know that the area of a circle is pi r squared. So treating fx as r, we can easily take the cross-sectional area of all the circles and then integrate them together to form the volume of the solid. This also works if you're doing it if you are rotating along the y-axis. You just have to make sure that you're using the inverse function and you're using y instead. Alright, so sometimes you aren't rotating about the axis, but that's alright, as long as you make sure that you do the translation properly. For example, for rotating about a horizontal axis, you minus or you add the constant to fx, whereas for a vertical axis you add or subtract it from the inverse function. And using this, you can easily find out the area. Now, in some situations, you also want to find out the volume of a solid that is formed in between two functions. So how do you do that? It's pretty simple. You just take this for the top function minus the one on the bottom function, and then you do the same thing. You use pi r squared, and you'll get the answer. Alright, finally let's move on to a volume of solid with specific base and cross sections. So this is rather simple. If you have to find out the volume is basically a definite integral from the cross section of the cross sectional area of whatever that is. So what does that mean? If you have a base, for example, and I say that the cross sectional area of the solid with respect to the x-axis is a semicircle, that means that you'll be cutting it up into a lot of semicircles. And so the expression for this semicircle will be this cross-sectional area. So for this example, we have y squared equals to 1 minus x squared. It's basically half a circle, and if the cross-sectional area is an equilateral triangle perpendicular to x-axis, then we can just use the area of an equilateral triangle, but substitute the lengths with the lengths that you see on the graph itself. Also, this also works for cross-sectional areas perpendicular to the y-axis. You just have to adjust the expression to fit it, and that's all.